Now remember, there are a certain set of words that can be used pretty much interchangeably as we progress. So say you're told that x equals a is a solution to a function that's equal to 0. We could not only call it a solution, we could call it a root, we could call it a 0, or we can call it an x-intercept. Now, solution and root are technically exactly the same word. They are synonyms, they are interchangeable. 0 and x-intercept have a little bit of an extra caveat to it. For example, a solution and a root is the solution to a function that's already equal to 0. So in other words, it's a function of a single variable that you have to solve for x. We call that a solution or a root. A 0 is when you have a multivariable equation, y equals some function of x. Find the 0 means set it equal to 0, and then find the solution or the root to that equation. X-intercepts, a little bit easier to identify. An x-intercept specifically has to do with graphs. So if I give you, for instance, a quadratic equation, that quadratic equation may not have any x-intercepts, but I guarantee you it's going to have solutions, roots, or zeros. Because, of course, if those solutions, roots, or zeros are imaginary, then they're not going to have any x-intercepts. So that word x-intercept technically means the same as the others, but technically it doesn't at the same time. Now, we can also use the word factor in there. We just have to make a little bit of an adjustment. Instead of saying x equals a, we say x minus a. So again, if x equals 2 is a solution to a function, then x minus 2 must have been a factor of that function. In other words, we get solutions from factors. If I have x equals a as a solution, then x minus a must have been a factor of that solution. The fundamental theorem of algebra. A very simple idea that has huge ramifications. If I think about linear functions, y equals 2x plus 7. X is to the first degree. It is a first degree equation. If I set it equal to 0 and solve, I get one solution. If I take a quadratic equation, set it equal to 0, I get 2 solutions. A cubic equation, set it equal to 0, I get 3 solutions. If f of x is a polynomial of degree n, then it has exactly n solutions. So no matter what the degree of the polynomial is, you know in advance how many solutions it's supposed to have because the fundamental theorem of algebra says so. So as you're working through a problem, start by assessing the degree of the polynomial. Then we can predict in advance how many solutions that we're actually looking for. That way at the end of the problem, we can count up our solutions and make sure we had exactly the number of solutions that we were supposed to get. Now, along with that concept comes the concept of multiplicity. Now, when we have a certain number of solutions, there's no reason why solutions can't be repeated. So if I have a quadratic, I'm going to have 2 solutions, but there's no reason I can't have 2 solutions that are the same number. I could have a quadratic x squared plus 2x plus 1, which would factor into x plus 1, x plus 1. Therefore, the 2 solutions would be x equals -1 and x equals -1. So I have 2 solutions, but it's not common to state both solutions. If they're both the same, we're only going to write it once. So we can just say that it has a solution of x equals -1, and we say that it has a multiplicity of 2 because it appeared twice as a solution, because multiplicity is the number of times a 0 appears as a solution to a given polynomial. So fundamental theorem of algebra says I'm going to have n solutions. If any of those solutions are repeated, we state its multiplicity instead of actually restating the 0 itself. Let's look at a couple of examples to illustrate what I mean by this. So the question is to find the zeros, then state the multiplicity of each. Or of each 0. So f of x equals 2 times x minus 1 cubed times 3x plus 2 times x plus 5 squared. So in general, if you're asked to solve a quadratic, for example, we set it equal to 0, and then we factor it out, and we set each factor equal to 0. That's going to be our general idea of how to solve a polynomial. We set it equal to 0, we factor it out, we set each factor equal to 0, and solve each factor individually. So what we have in front of here, you might be looking at and saying, oh my gosh, what did I get myself into? But then you realize, wait a second, this is already factored out for me. I have already factored it out for you. You're welcome. Yeah, we still have to set it equal to 0, but we don't have to factor it because it's already in its factored form. I've got a bunch of stuff multiplied together. Now, the common mistake on a problem like this is to completely ignore the directions and just do what seems right to do. It's depressing how often I see students look at a problem like this and start multiplying things out, start foiling things out to get it into a really long polynomial, and then you have no idea what to do with it. Well, what you're supposed to do with it is factor it. It's already factored. Just solve from here. Set each factor equal to 0 and solve. Now, before I do that, as I said earlier, I want to assess what the degree of this polynomial is before I do anything. That way I can predetermine how many answers I'm expecting to find. Now, to figure out the degree, of course, we could multiply it all out and look at that leading term to figure out what the degree is, but then I realize all I care about is the leading term. So let's just focus on the leading terms. For example, in this factor right here, the leading term would be x. And then I have 3x. And then I have x. So I can pretty much just ignore the non-leading terms and just multiply through what I have. For example, I've got x cubed. I've got 3x. I've got x squared. If I were to multiply it out, I would get x cubed times x squared. That would be x to the 6. Now, of course, I've got a couple of coefficients. 3 and 2 is 6 itself, but that's not really important either. What's important is the degree of the variable. X cubed, x, and x squared gives me x to the 6th. I have a 6th degree polynomial. If I have a 6th degree polynomial, that means I'm going to have exactly 6 answers when I'm done. So before I even get started, I see by adding up all the exponents, I have a 6th degree polynomial, therefore I'm supposed to have 6 answers when I'm done. So let's jump into it. Let's go ahead and solve this by setting each factor equal to 0. Now I'm going to point out to begin with that 2 is a factor. 2 is a factor, x minus 1 cubed is a factor, 3x plus 2 is a factor, x plus 5 squared is a factor. So I'm going to set each factor equal to 0, but then I realize 2 is never going to equal 0. 2 is a constant. It's 2. It can't equal 0 as well. So that leading coefficient really doesn't count. It really doesn't matter. I can ignore it. It's not part of the problem of finding the zeros. Now, when we get into graphing, that 2 is going to be important because, as we learned with lines and with quadratics, the leading coefficient is significant as it pertains to the shape of the graph. With lines, it represents the slope. With parabolas, we got our odd number pattern based on that leading coefficient, and it's not going to go away. But as far as finding zeros go, it's not important. Now, I'm going to take each one of these remaining factors and set them equal to 0. And I'm just going to solve each one individually. Now, realize x minus 1 cubed, if I cube root both sides, that cube is just going to go away because the cube root of 0 is still 0. Really, I don't have to think about it as x minus 1 cubed. I can really just pull out the x minus 1 and think about it as x minus 1 equals 0. So if x minus 1 equals 0, I get x equals 1. 3x plus 2 equals 0, I get negative 2/3. And then just like I did on the first one, that square really doesn't matter as far as finding the zeros go. X plus 5 equals 0, so x equals negative 5. So I have 3 solutions, yet the degree is 6. So where did the other 3 solutions go? Well, the other 3 solutions are right in front of us as well. Pay attention to the exponent to determine how many times that solution appeared. X minus 1 cubed really says x minus 1 times x minus 1 times x minus 1. So that x minus 1, that factor itself appears 3 times. So the solution x equals 1 appears 3 times. Therefore, its multiplicity is 3. So in other words, we get the solution from the x minus 1. We get the multiplicity from its exponent. So x equals 1 has a multiplicity of 3. Then we have x equals negative 2/3. That only appeared once, so its multiplicity is 1. And then x plus 5 appeared 2 times, so its multiplicity is 2. Easy as that. So here's another one. Why don't you try this one on your own? Hit play when you're ready. So once again, we can do this one the same way. We can imagine that the whole thing is equal to 0, and if the whole thing is equal to 0 and it's already in its factor form, I'm just going to set each factor equal to 0. So starting with this first factor out here, just like before, I've got a leading coefficient, but this time the leading coefficient has a variable attached to it. If I think negative 1/5 x equal to 0, I can't just ignore this whole thing because there is a variable. This can equal 0. If I divide both sides by negative 1/5, I'm just going to get 0 itself. So again, I can technically ignore the leading coefficient, but that variable itself is a 0 on its own. Anytime you have a lone variable out in the front of the function, that means x equals 0 is itself a 0. So I know I'm going to have x equals 0 from this guy. From this guy, I know I'm going to have x equals negative 3. From this guy, now keep in mind x squared minus 4 is a quadratic, so I'm going to be able to find 2 solutions out of this guy. I'm going to get x squared equals 4, square root both sides, x equals positive and negative 2. And then just like that guy, I can do the same thing with this guy, x squared plus 4. The only difference is this time I get x squared equals negative 4, and then when I square root it, I'm still going to get plus or minus 2. But square root of a negative, I have to throw in the imaginary unit I to compensate for it. So I have 1, 2, 3, 4, 5, 6 answers. But when I look at the degree of the function, I've got x to the first, I've got x to the fourth, I've got x squared, and then I have x squared squared, which itself means x to the fourth. So I have 1, 5, 7, 11. I have a degree of 11, but I only have 6 distinct answers, and again, it comes down to multiplicity. So once again, my answer of x equals 0, it appeared exactly once, so that's a multiplicity of 1. X equals negative 3 appeared 4 times, so that's a multiplicity of 4. X squared minus 4 gave me positive and negative 2, but remember, each answer, positive 2 and negative 2, themselves only appeared once at a time. Together, there's 2 of them, so because they came from a quadratic, but each one individually only had a multiplicity of 1. Although on the next pair, the 2i and the negative 2i, that factor was being squared, which means each solution appeared twice, so that would be a multiplicity of 2 apiece. So altogether, multiplicities added up, I would get 11, which matches my degree, so I know I've got enough.